Hello and welcome to another measurement and instrumentation class. In the previous class, we finished the concepts of power and energy and how we measure power and energy. Today, we're going to start with bridges, which is a very important part of measurement systems, especially on the sensor side. And we're going to start with the most famous one. You may have heard about it, which is the Wheatstone bridge. Now, and if we have time, we're going to start with the Wheatstone bridge. We're going to start with balanced and unbalanced, and then we're going to go to unbalanced Wheatstone bridge, and we will solve some practice problems. Usually on the FE exam, you would always have one question on Wheatstone bridge, and it's a very simple question that you can solve. And usually it's a balanced bridge. Now, Wheatstone bridge is connected as shown. It has 4 resistors. On each arm, it has 1 resistor. And at the middle, we have an ammeter or a voltmeter. So it could be either an ammeter or a voltmeter. And in this systems, it could be different configurations, but usually 2 of the resistors are known. One is a variable resistor and one is unknown. So in this particular example, R1 and R3 are known. So we know that, like, for example, R1 is 1K and R3 is 1K. R2 is variable and Rx is unknown. So again, our resistance R1 and R3 are fixed, known values. R2 is also known and it's variable. Usually, yes. Yes, I think, but I would double check to see if I'm modifying it every semester. So I've got rid of some parts like power factor correction because you're going to learn that anyway in power system analysis. So it's going to be a repeat. But this is a more important part. So I'm going to emphasize more on bridges, especially a Wheatstone bridge and shearing bridge and so on. But I will double check. So our resistance R1 and R3 are fixed. Known values and R2 is known, but it's variable. One thing else, I wanted to mention this. The reason that Rx is unknown, it's because usually Rx, we don't have access to it. So it may look like this is schematic, but imagine if Rx is a strain gauge sensor and it's connected to a bridge. So we don't sometimes have direct access even. It's like a black box. Imagine if Rx was a black box. We had no idea what was it, and we wanted to use the other resistors to determine the value of Rx. Now, in order to do that, we have to analyze the circuit and find a way to be able to, just give it a second. Just give me 1 second. Okay. So again, imagine if Rx is a black box. We don't know exactly what it is. It could be 2 wires just connecting to this part. And we want to determine this value. And we want to determine what is inside this. What is the resistance that we have at Rx? Now, in order to do that, we have to write the KVO, KCO, analyze the circuit. And one way to do that, to simplify that, is to make the system balance. Now, how can we make the system balance? I would explain more. First, we have to determine what current is measured in the middle. That's the reason we need the ammeter. So a voltmeter or ammeter is connected between these 2 nodes, node A and B. And the goal is to determine the value of the unknown resistance by balancing the bridge. Now, balancing the bridge means that the current passing through the middle branch would be 0. So IM is 0. And because IM is 0, VAB is also 0. In other words, VA is equal to VB. And this makes our job much, much easier. And I'll explain how. So the goal is to find Rx. To do that, we have to make the current that is passing through the middle branch, we have to make that 0. How can we make that become 0? By adjusting the known variable resistor. So this known variable resistor is a potentiometer, a pot, same thing that you saw in the lab. And you can adjust that, and you also know what the resistance is. So by slowly adjusting that, we can make the system balance, or in other words, we can make the middle current 0. Now, balancing the system means that IM is 0, therefore I1 would be equal to I2, because, again, according to Kirchhoff's current law, I1, the current going inside the node A, is equal to the nodes coming out of it. So I1 would be equal to IM plus I2. And because IM is 0, I1 would be equal to I2. And in the same way, because this current is 0, I3 plus IM in node B would be equal to IX. And since this is 0, I3 would be equal to IX. So this is for node B, and this is for node A. So I1 R1, if I multiply that, would be equal to I1 R1 would be equal to I3 R3. And I2 R2 would be equal to IX RX. Now, since I1 and I2 are equal, and I3 and IX are equal, we can write it like this. I2 R2 over I1 R1 is equal to IX RX over I3 R3. And since these are equal, I can just simply get rid of this and get rid of this. And what we are left with is R2 over R1 is equal to RX over R3. In other words, R3, R2 would be equal to R1, Rx. Or if I just want to find Rx, it would be R2, R3 divided by R1, or R1, which again gives us the unknown resistor. So Rx would be equal to R2, R3 over R1. Easier way to remember this is Rx times, or R4. So here it's R4, it could be Rx. Times R1 is equal to R2 times R3. So if you multiply the opposite arms together, you get a big X, okay? So you will multiply R2 to R3 and R1 and R2. So imagine that you have the multiplication sign, you just multiply the opposite ones and they should be equal. So R1 Rx should be equal to R2 R3. As simple as that. Even if you forget it on the FE exam, just drive an X and just multiply R2 to R3 and R1 with Rx. Now let's solve some practice problems. Some of these are directly from the FE exam. We want to find problem number 1. We want to find the unknown resistance for a balance bridge. Given R1 is 220 ohms, R2 is 330 ohms, R3 is 470 ohms. We want to find Rx, so the bridge is balanced. I'll give you a few minutes to think on this. Again, I'm going to just give you the equation. Rx would be equal to R2, R3 divided by R1 if it's a balanced system. Or other words, R1, Rx is equal to R2, R3. Okay, so has anyone solved it? What did you get? Yes, perfect. So R2 here is 330. Rx is R2 times R3, which is 330 times 470 divided by R1, which is 220, gives us 705 ohms. So pretty easy. If you get an example like this in an FE exam, it'll be pretty simple. It's a little bit tricky when the system is on balance, for example. Let's solve another example. Given R1 is 150 ohms, R2 is 100 ohms, R3 is 120 ohms, and R4 is 100 ohms. Vs is 12 volts, the source voltage. We want to find the output voltage. Now, the output voltage is this voltage V over here, or VAB. Zero? Okay. Yes. If the system is balanced, VAB should be zero. Is this system balanced or not? We have to first check. R1 times R4 should be equal to R2 times R3. You can do that. So R1 times R4 gives us what? 150 times 100. 15,000. R2 times R3 gives us 12,000. So they are not equal. Therefore, this system is unbalanced. Therefore, you're going to have a voltage passing through it. Now I want you to find what is the voltage passing through. I will give you, let's say, 5 minutes, and the first student to solve it gets a bonus point. Nope. How much? Yes. And assume that a voltmeter is an ideal voltmeter, by the way. What is the output voltage? Yes, the voltmeter's resistance is infinity. Has anyone solved it? Anyone else? No? I'll give you a few more minutes. Think on it. Okay. Do you want me to solve it? To make it easier, can I draw it like this? And this is my voltmeter. This is R1, R3, R2, and R4. Can I draw it like this? Yes. Now, if this voltage is 12 volts, what is the voltage between these 2 points? I'm going to call it 1 and 2 and 3 and 4. What is the voltage between 1 and 2? 12. What is the voltage between 3 and 4? Same 12. So I have 12 volts here, and I have another one that it's 12 volts, and it's connected here. Yes? Now, since this is an ideal voltmeter, means the current passing this is what? 0, because the impedance is infinite. There is a voltage, but the current passing it through. And this is a very important key. If there was a resistor here, you couldn't solve it using the way that I'm solving it now. So the current passing here is 0, and I want to just find the voltage difference between these 2 points, A and B. Now, to do that, VAB is going to be equal to VA minus VB. Now, what is VA? How can I find VA? I could simply do, this is VA. I could simply do a voltage divider. So VA is going to be R2 times VS, which is 12 volts, over R1 plus R2. Is that correct? Yes. What is R2? 100. What is VS? 12. And R1 plus R2 is 150 plus R100 is going to give 12,000. I'm sorry, 1200 over 250. What is 1200 over 250? I'm sorry, 4 point? Yes. I think, just give me 1 second to double check. Just give me 1 second. Yes, 4.8. Now, if I want to find VB the same way, it's going to be R4 times VS over R3 plus R4. And what is R4? It's 100 times 12 over R3 plus R4, which gives us 220. So this one would be equal to 1200 divided by 220, gives us 5.45. Okay, now that I have found VA and VB, I could simply VAB is going to be VA or VB minus VA if we want to find the direction as well, which is 5.545 minus 4.8, which gives us 0.65 volts. Is that clear? This is one way to solve it. Another way to solve this is, just give me 1 second. Another way to solve this is to do a KVO, KCO. So you can use the currents and do a KVO like in this loop and do another one in this loop. This is another one. Another way is to find just the currents, I1 and I2. So there are multiple ways to solve this. But the easiest way is just to use the voltage divider. Okay. Do you have any questions about this one? No? Let's go to strain gauge bridge. Now, the purpose of Whitson bridge is to use it as a strain gauge and measurements of usually pressure or strain in a system. So a variation of this circuit is used with a strain gauge to measure the deformation of an object. The strain gauge sensor looks like this. We have two identical resistors on the opposite arms. So R and R are equal, and then we have R plus delta R. Now, the output of a strain gauge, VO is going to be, or V0 is going to be VB minus VA. And using the same principles that we use for the voltage divider as the example that we had. VA, or I'm sorry, VB or VA, both of them are the same, is going to be here equal to, which is this voltage. It's going to be equal to R plus delta R times Vs over R plus delta R. And VA, which is this voltage, is going to be equal to R times Vs over R plus delta R. So this is our VB and this is our VA. Same thing that we did for the previous one. So V out would be VB minus VA. Again, the same way that we solved the previous example, we use the same concept for this. Again, this is with the assumption that the middle branch is open circuited, meaning no current is passing. It has a voltage, but there's no current passing. If you had a resistor here, it's going to be a complete different story. You cannot use this equation. You have to do loops, KVL, KCL. You're going to have 3 unknowns. You have to do a matrix. It's going to get very complicated and messy if you add a resistor, because then you're going to draw current in the middle and all the current would not pass through the lower arms. And that's going to be a different animal. Okay. Now, this equation, because you have the same denominator, you just add the denominators together, or in this case, subtract them. So this and this would go, and we are left with Vs delta R. So Vs delta R would be left, and the denominator would be the same. So add it. So V out would be Vs delta R over 2R plus delta R. And in this case, if delta R is much smaller than 2R, in other words, if the changes are very small, we can further simplify it as V out is going to be Vs over 2R delta R. Therefore, we have usually a table. We know how much change in the pressure causes how much change in the output voltage. And it's usually linear. If you put too much pressure strain gauge, it's going to rip apart, and then it becomes nonlinear. But usually it's a linear relation between V out and the changes in delta R, which are the strains. Again, a strain gauge, delta R, R changes with rho L over A. Rho is comes from the material of the resistor. It's the property of the material. If you have copper, it's going to be, lower. It's and so on. L is the length, and A is the thickness. Okay, and sometimes we write it as L A over A rho. Again, thickness. Yes, yes, yes. So this is A, or the area, and this is L. Longer it gets, you're going to have a higher resistance. When you stretch it, the strain gauge, it becomes longer and thinner. So if I stretch this, it becomes this. It's thinner and longer. And you're going to increase the resistance. That's how a strain gauge works. And therefore, you're changing this delta R. Now you can determine that with V out, and you can match that with the amount of stretch that you have, depending on what type of. Some strain gauges have limited, movement. You can't stretch them too hard; it's going to just rip apart. Some other you can stretch them, pretty far.
Can I see slide 14 for just a second?
Yes, of course. Yes, voltage B minus voltage A. V out is VB.
So over the left, you have VB written as R plus delta R times VS
Yes.
plus delta R. Do those not just factor out at that point?
No, this is R plus delta R. If I had just this, they would factor out.
I'm sorry, over on the left side, the stuff that you wrote down.
Oh, I'm sorry, I didn't do R. Yeah, thank you. Yeah, forgot this one. I'm sorry. Thank you. Yeah, I forgot one of the R. It's going to be this over the entire of this. So it's R plus delta R plus R, which is going to be 2R plus delta R. And here it's going to be 2R again. Yeah, I forgot it. Thank you for. Yeah. Again, 2R plus delta R. Here, 2R plus delta R. Yeah, it's a typo. Yeah. Now, let's solve a practice problem for this. So for this particular example, R is 1K. Delta R is 5 ohms. Vs is 10 volts. What is V out? What is it? Have you found it? Okay, give you a few more. So since 2R is much greater than delta R, 2R is 2000 and delta R is 5 ohms. So it's much greater than 5. I can use this equation. I can utilize this equation. V naught or V out is going to be Vs, which is 10 volts, over 2 times 1000, which is 2000, times delta R, which is 5 ohms. So it gives us, the first part is going to be 0.005 times 5, which gives us 0.025. In other words, it's 25 millivolts. And usually the voltages are around this. Now, usually the factory gives us a data sheet and says each like 5 millivolts is equivalent to, if you want to measure air pressure, it's like 1 bar or 10 ps, something like that, 1 psi, for example. So if you have like 1 millivolts, it's going to be 1/5 of that. And this is also used as a thermocouple. Resistor, obviously resistance also changes with temperature. So if you change the temperature, you're going to change the resistance, therefore you're going to change the output voltage. It is also used as a photodetector as well. So we have these thermistors, we have these photoresistors that I can replace it with these arms, and I would show you, we have a lab that's specifically dedicated to this. We're going to have it next week, that we're going to replace one of the arms with a strain gauge and then with a photoresistor, and you can see that changing that photoresistor, I would show you what, you can use your phone's flashlight, and you put the flashlight on it, this delta R would change and the output voltage would change. And you can code your Arduino and say if the voltage is above a certain threshold, you're going to turn off the light, and if it's below that, you're going to turn on the light. This is exactly how so you can connect this to actually a Arduino, or without even an Arduino, you can have a limiting, switch and a triggering threshold switch, and you can say like a pull push, amplifier or an op amp. You can connect it to that, and the other input of the op amp you can connect it to a threshold voltage, and if the voltage is higher, it would trigger a relay. If it's lower, it's going to disconnect the relay. And this is how actually you build a dawn to dusk, or dusk to dawn, I'm sorry, light system. Again, you can use a microcontroller, or you can just simply skip that. So there are a variety of different applications that you can use this, and I will show you how we utilize it in the lab, in real world. It's used a lot, actually. Now let's solve some practice problems. These are for sensor resistance change in an unbalanced bridge. So a strain gauge is used in one arm of a Wheatstone bridge. The previous one was like 2. Now it's just in one arm. Given R1 is 120, R2 is 120, R3 is 120, and R4 is 121. So just a 1 ohm difference. And Vs is 5 volts. We want to find the output voltage. So again, imagine we have the bridge, and we have identical resistance in each arm. But the one that is connected to the strain, this one, is 121, measured at 121. And the source voltage is 5 volts. We want to find this output voltage, V out.
What is
And now again, our next class, I would solve problems that has a resistor in the middle as well. Yes,
what order of magnitude should delta R be smaller than 2R?
100 times.
Okay.
Well, yeah, 100 times. Again, I'll give you 5 minutes to solve this, move on to the next one. Do you need more time or do you want me to solve it? More time? Okay. What is the answer? Oh, I got something different. Let's solve it. So again, V out is going to be VB minus VA. So this is VB, this is VA. So V out would be VB, which is 121 times 5 over 121 plus 120. And VA is 120 times 5 over 120 plus 120. So what is 121 over 241? 121 times 5 over 241? It's 2 point, this is what I got. Please double check it. 2.5105 volts. And the second part, 120 times 5, it's going to be 600 over 240, which is give us 2.5 volts. Now 2.5105 minus 2.5 volts gives us 10.5 millivolts. So you can see that it's very small, very, very small change in the voltage with a 1 ohm change in the resistance.
Is that because it's not balanced?
Yes, because it's not balanced, it's slightly unbalanced. So imagine you have two pipes, one of them is slightly, thicker and passes a little bit more water than the other side. So if you connect these two together, you're going to have a small water passing from one branch to another. Can I go to the next one? Yes? No, because this is the total. It's 120. We want to find this voltage, VA. VA, and don't just forget about the right part when you do that. It's going to be 120. It's resistance over the total resistance over 240. That one is going to be 120 over the total one, 120 plus 121. Divider, yeah. Now, find the current in each branch of an unbalanced bridge. Given R1 is 100, R2 is 200, R3 is 150, and R4 is 100, and VS is 9 volts. Assume the output is measured by a voltmeter with a very high resistance, so no current flows through the meter branch, and we want to find the branch current as well. So again, R1 is 100, R2 is 200, R3 is 150, and R4 is 400. I'm sorry, R4 is 100. This is 100, 150, 100, and 200. And we want to find again this voltage. and this is 9 volts. How much is the voltage? Output voltage? Has anyone found it? Anyone? So 9 times 200 over 300, which is going to be 1,800 over 300, gives us 6 volts for this. And 9 times 100 over 250, it's 900 over 250 gives us 3.6. So 6 minus 3.6 gives us 2.4 volts. That's V out. Now, if they were connected, we want to find the current passing through this one, and then the difference between them would give us a current if they were passing. Now, this current, I'm going to call it I1. This one I'm going to call I2. I1 would be Vs over its resistance, which is 100 plus 200. So it's going to be 9 over 300 gives us 30 milliamps for I1. And I2 would be 9 over 150 plus 100. So 9 over 250 gives us 36 milliamps. And the difference between them, it's going to be 36 minus 30, gives us 6 milliamps approximately. But it will make the whole system go in a different direction. I will explain why. Let me give you one till we have a little bit of time. A nice example of an unbalanced system. With a resistor in the middle. So imagine we have this circuit, we have R1, R3, R2, and R4. Which are connected to a voltage source, Vs. But in this case, we have a galvanometer in the middle, and I'm going to call it RG. Now, if R1 is 100, R2, let's say it's 200, R3 is 150, R4 is 100, and RG is equal to 50 ohms, and BS is 10 volts. We want to find the midpoint voltage, these two voltages, VA and VB. We also want to find the current through the galvanometer or IG. So we want to find VG and IO. VO. VG is actually VO. So we cannot use the voltage divider at all. Why? Because we have a current passing this. IG is not equal to 0. Therefore, I1 would be equal to IG plus I2, and I3 would be equal to I3 plus IG would give us I4. Therefore, we cannot use the voltage divider equation. We have to find another way to solve this. I'll give you a few seconds to think on it, a few minutes. If someone comes up with a solution, I'll give them extra points. If not, I would solve it. Now, IG here is VA minus VB over RG. So we need to find VA and VB. We already have RG. Or we can directly find the current. Has anyone solved it? Need more time? Do you want me to solve it? Yes, or you need more time? 5 minutes? Okay. Do you want me to solve it? Okay. So there are two ways to solve this. One is to use a KVL in each loop. Other one that I prefer is to use a KCL in each node. So we have two nodes, node A and B. At node A, VA, if I want to write it, it's going to be VA minus VS over R1 plus VA minus 0, because this is technically ground, minus 0 over R2 plus VA minus VB over RG, it's going to be equal to 0. And at node B, same thing, VB minus VS over R3 plus VB minus 0 over R4 plus VB minus VG over RG is going to be equal to 0. To make it easier, I have assumed that all the currents are going inside the nodes. Writing it that way will correct itself at the end. Because if you have a negative current, it means the current is going in the other direction. Now, two other equations that we have, V out is VA minus VB. We can write it the other way as well, but again, if the voltage becomes negative, it means it's in the opposite direction. And IG is equal to VA minus VB over RG. Now, so for the given example, for node A, we're going to have VA, which is unknown, over VS, which is 10 over 100, plus VA over 200, plus VA minus VB over 50 is equal to 0. Now what we can do is I can multiply everything by 200 to make it easier. So we're going to have 2 times VA minus 10 plus VA plus 4 times VA minus VB would be equal to 0. So 2VA minus 20 plus VA plus 4VA minus 4VB is equal to 0. So 2 plus 1 plus 4 gives us 7VA minus 4VB is going to be equal to 20. So this is our first equation. Call it equation number 1. Now our second equation, it's for node B. It's just going to be VB minus 10 over 150 plus VB over 100 plus VB minus VA over 50. It's better to multiply this by 300. Gives us 2 VB minus 10 plus 3 VB plus 6 VB minus 6 VA equal to 0. Just give me 1 second. Come back. Okay. Now it's going 2 VB minus 20, and then we have 3 VB. And if we add all of that, it's going to be 11 VB minus 6 VA is going to be equal to 20. So one equation here, equation number 2 here. Now to solve the problem, 2 equations and 2 unknowns, 7 VA minus 4 VB gave us 20. Negative 6 VA plus 11 VB gave us 20. What can we do? We can add them together. So this is one way to do it. Or we can subtract them from each other. Let's see which one is better. Let's do another thing. Adding them gives you VA plus 7 VB. It's equal to 40. I mean, you can find VA and VB in relation. Or let me try another way. Let me try an easier way. So from the first one, VA is equal to 20 plus 4 VB divided by 7. Is that correct? And if I substitute this one into the second one, so I will replace this into the second one, negative 6 times VA, I'm going to replace it with that 20 plus 4 VB. I'm going to make it easier. So 20 plus 4 VB divided by 7 plus 11 VB gives us 20. So negative 120. If I multiply, let's multiply everything by 7 to make it easier. So negative 120 plus minus 24 VB plus 77 VB is going to be equal to 140. I multiply by 7 to get rid of that 7. And 24, negative 24 plus 77 gives us 53 VB. And I'm moving 120 to the other side, gives us 260. So 53 VB is going to be equal to 260. Therefore, VB is going to be equal to 260 divided by 53. Going to be close to 5. Can someone calculate this? I think 4.9 something. Yeah. 4.91. If I round volts. Now, for the second one, we can do the same. We already know what VB is. I'm going to replace it by 4.91 in this. So VA would be 20 plus 4 times 4.91, let's say, divided by 7. Can someone calculate this? 2 plus 4 times 4.91, it's like, I think 19 something, 19.6 or 7. Was it? And the total would be 39 point something. What did you get for the denominator?
5.66.
What? Oh, the total, the final answer. What is the denominator? I think it's 39.64 divided by 7 gives us 5.66 volts. Now, if I want to find the current passing through the galvanometer, it's going to be 5.66 minus 4.91 divided by 50. Can someone calculate this? It's probably going to be 0.75 divided by 50, which is around 0.015. What is the actual number? 5 amp. 75 divided by 50 is 0. Yeah, 0.15. Or in other words, it's 15 milliamps. And what is V out? Is 5.66 minus 4.91, which is 0.75 volts. So 0.75 volts and 15 milliamp is the answer. We are out of time, actually. Yes. Yes. Okay. Thank you so much, and I would see you next week.
Go back one more slide, please.
Yes, sure. Just give me a second to stop the recording here.